All right, Pascal's triangle. Pascal's triangle, and you might have talked about, it's a pattern. You may have talked about it in like science class, because a lot of things out in the real world actually go off of this pattern. Stuff like some of the leaves on plants, I think like pineapples. You know how the leaves on pineapples come up and out? They use this pattern. You'll have like one leaf, then you'll have a leaf and a leaf, then they'll start going up like this does, and the circle's out. All right. If you ask them in science class, they'll just the pattern, or if you even if you look this up, say Pascal's sequence in nature, it'll show you different things in nature that grow that way and work that way. What is the pattern here?
They add outside.
Okay, so the two boxes right next to each other get added.
They would equal 5.
Equals 5, so 5 goes right there.
And then the 1 would.
1's out there, right? 5. Add these two up, what do you get right here?
10.
This is where you were doing it right in here, Jaden. Then when you were getting in here, you were messing up. What do we get right here?
10.
Here?
5. 1.
1 here again.
6. 15. 20.
What here?
7.
Here?
21. 35.
Notice once we get to the middle, starts going back down. Every other row, you'll have a new number introduced in there that you have to add in.
21.
That is 56.
70.
That's about as far as I'm going to go. So it just continues down that way. Keeps adding on the next part. Add the 2 blocks, gives you the block that they're hooked to. Add these 2 blocks, gives you that block that they're hooked to. Add these 2, gives you that one. Add those 2, gives you that one. So on and so on. What we're going to cover today deals with patterns. All right? And we're going to talk about different kinds of reasoning, inductive and deductive reasoning. Inductive reasoning is this: seeing a pattern and using that pattern to come up with solutions. Deductive reasoning is more using stuff like rules and theorems and postulates and laws to come up with a conclusion. All right, open up your books to page 71 and have your homework out. We're going to do a couple of these together, then I'll ask some questions, or ask 4 questions that you want to see. Number 19 on 71, apparently it looks something like this. And I think I told you last time, converse, inverse, contrapositive is very important. For some reason, the last couple of years, I put a statement on the test for chapter 2 for this chapter. In the other book, it was a different chapter, but put a test for this chapter where we're talking about all this logical thinking and reasoning. And 2 or 3 of the problems on that test are write this in an if and then statement. And everybody seems to have trouble with it. So I want to make sure that we cover that. If I gave you a statement, something like, let's see, just making up something crazy. John went to the fair on Friday. How could we make that an if and then statement?
If John went to the fair on Friday.
Say it again.
If John went to the fair on Friday.
If and then statement. What's it got to have in it?
If John went to the fair, then it is Friday.
If John went to the fair, then it is Friday. I would accept that as an if and then statement. Is there another way that you think I might accept?
It is Friday, then John went to the fair.
Say it one more time.
If it is Friday, then John went to the fair.
If it is Friday, then John went to the fair. Now that turned it around, and you got to be careful turning it around, but on a statement like this one, I wouldn't mind so much. All right? Let's see, let's think of something geometrical here. Angle 1 and angle 2 are vertical angles. We might have to add a little bit to that, but what kind of if and then statement could we write using that? What do you know about vertical angles? They were saying they're congruent, right? So what kind of if and then statement could we write there?
If angle 1 and angle 2 are vertical angles,
Everybody hear what Harry said? If angle 1 and angle 2 are vertical angles, then they are the same. Or then they are congruent. Now down here, how are we going to write this one as an if and then statement? If what?
If you do your homework, then you.
And I'm going to shorten this up a whole bunch because I do not like to write. If you do homework, don't forget you got to have the if and then in it. Otherwise, it's not an if and then statement. Then what?
Then you do good.
Then you do okay on test.
Feels like you do English.
What did I say last time? Didn't I say not say that? I said it was going to be a detention.
No,
thought
I don't
said-
remember that.
Wait, what?
Don't mention the fact that it's not math. Yeah, it is math because you're thinking logically. Converse. What's the converse do to the statement? Anybody remember that?
It's around the same.
Switches it. All right, switches the hypothesis and the conclusion. Doesn't change the if or the then. So what's the converse going to say this time?
If you do okay on the test, then you did your homework.
So if you good on test, just because I don't like to write. If you good on test, then what?
You did your good on.
Then you did homework. All right, so let's go back because I forgot to do the true or false here. Now let's just wait till we get all the way done, then we'll go back over. Inverse. What's the inverse do to a statement?
Makes it opposite of that, so if you not
It negates it.
All right, negates both parts. Negates the original. Go back to the original. Don't go to the converse. So if what?
If you don't do your homework,
Don't do homework.
then you don't do your homework.
Then No good, test. Don't write like me. Contrapositive, what's the contrapositive do?
It's calm.
That's good.
Alright, switches it and negates it. So what's it gonna say?
If you don't use it on test, then but if you,
If no good on test, then what? Then didn't do homework. Now, we want to say whether these are true or false. On these, can you say for sure if they're all true or false or not? Not really. It's not going to work out right, but we're going to try anyway. If you do your homework, let's say that you're being practical here, not just being a smart aleck. If you do your homework, you'll do okay on the test. Is that true or false? I've said that several times, right? If you don't do the homework, you're probably not going to do very well on the test. Got to do the homework. That's the practice. Converse, if you play for any athletic team, if you don't go to practice, you'll do well. Molly goes out and she just decides, I'm not going to practice for the next couple weeks, and then she goes out and runs. You gonna run well? You'll probably be tired and sucking wind about halfway through, right? Converse. If you did good on the test, then you must have did your homework. True or false? Is that necessarily true? Probably. But now, are there some of you that can do well on the test and not really have to put a whole lot of effort into the homework? Yeah, there's people like that. Inverse. If you don't do the homework, then you probably won't do good on the test. True or false? Right, true again. If we're just using common sense here, right? Now, if I ask you to tell whether something's true or false, it's going to be a more black and white thing. Either it's true or it's false. There's not going to be any of the gray in between on something like this one. How about the last one, the contrapositive? And remember, we said if the original statement's true, what do you probably know about the contrapositive? It's probably true also. So converse switches the hypothesis and the conclusion. Inverse leaves it in the original order, but negates both parts. Contrapositive switches and negates. Problem 66. What they ask you for? Next three numbers?
I don't have the answer. Can I use the restroom?
They ask you for the next three numbers?
Next two.
Next two? But hurry. What are the next two numbers?
9/11.
How about 67?
56 and 67.
Everybody agree with those two? A little tougher one on 68.
Like the multiplying the top fraction by 2, bottom by 2.
Multiply the top by 2, bottom by 3. Very good. What happens with this first one, though? This is what confuses most everybody.
2/1.
It's 2 over 1. Sometimes you might have to manipulate stuff around just to make it make sense to you. So we multiply the top by 2, multiply the bottom by 3. So if we multiply this by 2, what's that going to give us? 32. Multiply this by 3, what's that give you? 81. Multiply this by 2, what's that give you? 64. That by 3, what's that give you? 243. Sometimes you might have to do something like that. And I like patterns like that. So, let's see if I can come up with another one here. Can't think of anything off the top of my head. Better just quit before I look silly. How about this one? If I get it, a little tougher.
25 and 34.
25 and what?
36.
Now, the difference here, these first two, arithmetic sequences, because they just go up or down by the same amount. Alright? This one here, we're multiplying by something, not an arithmetic sequence. This one here, not an arithmetic sequence, and that's usually what makes this one a little harder. Somebody explain to me what was going on there.
That's squares.
These are the squares. Alright, so 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, so on and so on. Anybody see a different pattern in there maybe? Because I've seen it differently. That's the pattern everybody's seen was the squares. You added a different number each time. What I add this time?
3.
3. What I add this time?
5.
What I add this time? 7. So what would I add the next time? 9, 11, so on and so on. Either way, it still works out the same. Whether you say, okay, that's all the squares, or you're adding 2 extra each time to the number you're adding to it. So be able to pick out different stuff like that, different patterns. On this, on 39, look at 39 real quick. That arrow, I might have forgot to mention it last time, I'll use it every now and then. That arrow just means implies. And all that means, it's just like all the other stuff that we had, but it's just another way to write it. So don't let that confuse you. You'll see me throughout the year. I do it all the time. I'll do something like what's that mean when I write something out that way? Acute angles between 0 and 90 degrees. So if an angle's acute, that implies to us or tells us it's got to be between 0 and 90. Don't make the arrow harder than it is. What they have in this box on this one? Is that what they had in there? 39? No, they didn't have. They said draw the truth table. Is that what they said? All right. What are we going to put in this box? P. Don't make these truth tables harder than they are. P could be what? True. Remember on the first part of the box, we said you go what pattern? True, false, false. You could go opposites, true, false, true, false. I just like to keep it this way. That way, every time we see one, we're doing them all the same way. Let's jump to this box if we do Q. If P is true, Q could also be what?
True.
True. Notice there how I led you right into that? Because that's what I want right there. If P is true, what else could Q be?
True.
So we got a true, true, we got a true, false, now we got a false, true, and a false. That way we're matching them up all the different possible ways. If you were doing a 2-question true and false test and you had no clue what was on the test, you didn't study for it, and you had to guess, these are the 4 answers you could give on that test. You could say both of them are true. You could say one's true, one's false. You could say one's false, one's true. You could say both of them are false. 4 different ways. Here, I'm going to put, what's that symbol mean again? Not P. If P was true, what's not P? P was true, what's not P? False. P was false, not P is true. False, true, right? Then out here, this is going to be our final thing that we're saying here. Not P implies Q. I messed up. Where are you confused at? So, do we know what P stands for? That's what we probably should have said first because she wasn't in here last time, right? We don't have a clue what P means. We don't have a clue what Q means either. This is like some statement. The floor is green, all right? Who knows what the statement is? It doesn't matter. What we're trying to figure out is, when we look at this statement right here, is it more likely that this statement's gonna be true, or is it more likely it's gonna be false? We can't say for sure which one it is, because we don't know enough information. But we can get a better idea by making this truth table. All right? So with this, is this what 39 says, or did I just write it? So with this, when we look at these two, we got a false here, or a false here and a true here. What's that tell us about the whole statement? Everybody agree with that? How about a false and a false? What's that tell us? How about a true and a true? How about a true and a false? What percent of the time is this statement false?
75.
And what percent of the time is it true?
25.
25.
So how did you get?
Because, and this is something I should have said last time, that's like, if we know this, then that implies that, and I didn't, last time we talked about and or. If it's and, both parts have to be true for the whole thing to be true. If it's or, only one of the two parts have to be true.
So
Alright?
how do you know what to choose if you?
If it gives you the arrow like that, that's the and. It's got, the whole thing's gotta be true for it to. Alright, and I didn't say that
okay,
last time,
gotcha.
I should've said that, shouldn't I? I forgot this
I
book
get it.
uses the arrow instead of.
So if there's false in it and it's not true too, then it's false.
For and.
Yeah.
For or, alright, so I could say something like, Dawson is a boy and a horse. Alright? That would be false, right? Because he's a boy, that part's true, but he's not a horse, so that part's false. So the whole statement is false. But if I say it a different way, I say Dawson is a boy or he is a horse, then the whole statement is true because he's one or the other, he's a boy. That makes sense? How about, go ahead. We're gonna make a list of statement for you. How about any of the others there, 40 through 44? Everybody sort of understands the truth tables. We're not gonna do a whole lot with truth tables. I really don't care that much about them, all right? The whole thing, the main thing is making sure you can think things through logically and know that if you have and in there, then it's gonna tell you both parts have to be true for the whole statement to be true. If you have or in it, only one of the two parts have to be true. Other questions? Other things off that page you wanna see? Huh? You want me to do another? Which one? 40? Problem 40. Not Q implies P. Not Q implies P.
Isn't it the exact same thing, just without different letters?
Yep. So that'd be just like this, except what's gonna be the first letter here? Q. What's gonna go here?
Not you.
Not Q. What's gonna go here? They didn't tell us anything. I'm not reading the directions or anything. They didn't tell us like Q is this or P is that, right? So it's this again. Oh, I'm sorry, I should have changed this. That's not Q implies the letters around on it. Other questions?
I was just gonna say,
Sit outside with their paper
Can
cup.
I say something?
No.
Yeah, please, cause I'm done.
You're done for the day? Go to sleep.
Seriously?
Yeah, you're right. Then, how come see, look, somebody else said that, not me. That ought to tell you something. Start copying this down. Reasoning, that's the title. We're going to cover inductive and deductive reasoning. If you want to write quickly because I'm switching the slide. So, inductive reasoning, deductive reasoning. Two different kinds of thinking something through. Make sure you're keeping your binders. Some of you are going to be upset. Last year it was this way too. Going to be a lot of people upset when I collect binders because the way I grade them. Put the title on it, on the notes each day. That way I can find it easy. And keep all the notes right there in that one section in your binder.
How many sections?
Yeah, they should be in order.
All I have is knit and.
Should have notes, postulates and theorems, tests and quizzes.
Like, I put my notes on.
Gotta be a binder.
How's it gonna be?
Can we just like spend one day like figuring the binder?
Maybe.
Well, like 30 minutes.
Write this down.
What was that second?
Deductive reasoning. Deductive reasoning. I can't remember which one came first.
Reasoning went first.
Inductive reasoning came first, right? Yeah.
That had nothing to do with education. Really takes my ears. Yeah. A little rusty.
You might want to write this down somewhere in your notes. Dislike this book because I got used to teaching out of the other book. Again, that arrow means implies. If you see a double arrow where it's going both ways, that means the statement should work both ways. And we talked last time about biconditional. That's what is biconditional.
So would that be like with the or?
Biconditional means it works both ways. So P implies Q
And Q.
and Q implies P. So it works either way. This one just says P, like P implies Q. So if we had something like, let's go back to Dawson here. If we had Dawson implies boy. That's true, right? But if we turned it around, is that necessarily true? No, because there's other people who are boys, right? But if we did this, if we put that double arrow on it, then what we would be saying is Dawson is the only boy. So Dawson implies boy, boy implies Dawson. And there's no other way that we could, no other statement that could be true.
What about the double arrow on the bottom? Is that the
Same thing.
So, maybe true.
No, well, not in real life, because Dawson's not the only boy. But if they tell you something, you know, if you're looking at something and it says A, B, then we know A implies B. If they put a double arrow on it, then we just accept that it's true for whatever we're going to do with that after that. If that's like our original statement. Does that make sense? So if they're saying, I'm telling you this, what conclusions can you draw from it? A conjecture, and you'll be asked to make conjectures about stuff. A conjecture is a statement based on your observations. All right, so if I draw an angle up here, and I say make a conjecture about that angle, what might you say?
It is a right. It is a acute angle.
It looks like it's an acute angle. That's a conjecture. Do we know for sure that it is? No, but we're drawing that off of what we see. That's what a conjecture is. Something that you draw off of observations. Inductive reasoning. Inductive reasoning, if you wanted to write something down with inductive reasoning, one word for inductive reasoning, patterns. Inductive reasoning always deals with patterns. So inductive reasoning, you see a pattern. It doesn't have to be numbers all the time. It could be anything. Right? It could be something where Molly comes tardy to class just about every day. She's walking through the door just as the bell rings every single day. So come Thursday, when I see you guys again, I'm getting ready to shut the door because the bell's ringing. And then I use inductive reasoning, and I'm over here and I go to pull the door shut and I think, and I open it back up because I'm using inductive reasoning thinking Molly's going to be walking in a minute. So seeing things, seeing a pattern. Maybe you ride the bus and you know your bus driver for whatever reason is late every Monday morning. So instead of going out there and standing and waiting for 5 minutes, because instead of coming at 6:50 on Mondays, they come at 6:55 every Monday. Well, on Monday then you might what? Stay in the house an extra 5 minutes. All right, that's probably true because they're supposed to stop and wait, but I know sometimes that they just fly on by.
That happens to me, like,
And
I don't
after the
ride the bus
first week,
usually, but one day I ride the bus, but I wasn't outside for 1 second, and then they just left.
They didn't even like honk their horn anymore, I think.
Yeah. They
But
usually don't.
usually in those areas, like especially like the smaller town areas like West End, they get irritated, like the neighbors are like, oh my God, stop honking that ridiculous horn. Huh?
Now, with my sons, it annoys me sometimes because if they're not going, the bus driver that they have will sit out there and honk for like 10 minutes. And I'm
But it's
like,
supposed to be 30 seconds.
I'm like, are you serious? There's a reason, you know, normally if my sons are riding the bus, they're standing out there waiting on you. If they're not out there, they're probably not going. So see the pattern, but I know that's what the bus drivers are supposed to do, so. Numbers such as 3, 4, and 5 are called consecutive integers. Make a conjecture about the sum of any 3 consecutive integers. So what I want you to do, just there on your paper somewhere, pick 3 consecutive integers, and I want you to try to come up with some kind of conjecture, some kind of thought, and try to make it like you have some brain power. Don't just say they're in order. Well, no kidding. That's why they're called consecutive integers. They're numbers. That doesn't take any brain power whatsoever. Come up with something. Pick 3 consecutive numbers and try to come up with some kind of conjecture you can make about them. Anybody come up with something? Tell me.
I said 7, 8, and 9. They add up to more than 15.
It's true, that's a conjecture. All right? Anybody come up with something that would work for any 3 numbers that we pick?
I'm not sure if this would work for all of them, but for the ones I've done the math for so far, it seems like usually they equal an even number.
So if you take all 3 consecutive numbers, they add up to equal an even number? I don't know, let's try a few. Give me 3 consecutive numbers.
1, 2, 3, 9,
1, 2, 3, 9, 9, 9 is not 3 consecutive integers.
5, 6.
What's 1, 2, and 3? 6.
4, 5, 6.
Now, when you do this, when you're looking at this stuff, do I just want to keep picking numbers the exact same way that I picked them here? No, you probably want to pick something a little different every now and then to make sure that it's going to work for everything and not just one. So somebody said 4, 5, and 6.
equals
Yeah,
15.
is,
What's that equal?
15.
15.
they have to have 2 odd numbers in the sequence.
There's not too long than that.
No, I'm talking about for it to add up to an even, it has to be 2 odd numbers.
My bad.
And then to add up to an odd, there's 2.
So if there's 2 evens,
That's
they're going to add up to an odd. If there's 2 odds, they're going to add up to an even. We could say that, right? Anything else? Nobody's got anything else? Just when I was looking at it up here, and I don't remember if there's any certain answer to this or not. When I was looking at it, I was thinking the first number plus the third number equals twice the second number. Does that work?
Or the second
Yes.
number times the third number would equal
Oh,
like for 1, 2, 3.
Now make sure it works for them all though.
5, 4, 5, and 6.
So what I said is
10.
4 plus 6 is 10. Double that, 10. So that would work. That'd be a pattern, something that you could use. Anything else? So consecutive integers. First of all, main thing here, you got to know what consecutive integers are, because we're going to do some problems. And if I say you're given 3 consecutive integers and they add up to 12. This is going to sort of be like the angle problems. And what we can do, first number, second number, third number. If we don't know the first number, what are we going to let it be? X. Now here's where everybody gets confused. Let the first number be X, because we don't know what it is. Are we going to let the second number be Y? No. If they're consecutive integers, what's that next number going to be in relationship to this X?
X plus 1.
X plus 1. What's the third number going to be in relationship to that X?
X plus 2.
X plus 2. Then I said the 3 of them add up to 12. Could I set up an equation from that?
Yeah.
The first number plus the second number plus the third number
So I guess 12 minus 3
equals 12. Get 3x. Mine's not going to work out very well because I just made up something in my head. Oh yeah, it worked out all right. 3x equals 12. Subtract 3 on both sides. You end up with x equals 9. What's x equal?
3.
So x equals 3. What's our 3 numbers? 3, 4, 5. What if they said this? Consecutive even integers. How would that change it?
2, 4.
It wouldn't be 3, 4, 5, right? No, never mind. I was thinking different.
Consecutive even integers would mean that you don't want 3, 4, 5. You want like 4, 6, 8. You want to skip a number in there. What if it said consecutive odd integers?
3, 7, 3, 5, 7.
3, 5, 7, 9, so on and so on. Let me erase this, see what it is here. 3 plus 4 plus 5, this is the pattern that apparently I wanted you to come up with. What's happening each time? It's getting bigger, that's true. The sum will be 3 times the middle number.
4, 8,
What's 3 times 4? 12. 3 times 8? 3 times 11? Let's pick 3 other numbers, see if it works out.
110, 111, 112.
Say it again.
110, 111,
110, 111, 112. The conjecture that they made about this is that 3 times that, which would be 333, should equal the sum, right? What are those 3 add together? 333. So 3 times the middle number gives you the sum. Counterexample. Counterexample is an example that shows something is not always true. An example that shows something is not always true. It's a precise example. All right, don't just say, oh, there's lots of them. No, if I ask you for a counterexample, I want you to give me an exact example. So if I say, all students in the Brown 3 geometry class are 17 years old or older. Don't just say, no, that's not true. Give me a counterexample to show me it's not true.
Look at that bang right there.
So give me the counterexample.
Kiara is 16 years old.
Kiara, that's all I need is the counterexample. That's a counterexample, that one example. Alright? Don't put down, there's lots of people in that Brown 3 class that are less than 17 years old. A counterexample is one example that shows the statement is false. Deductive reasoning. Inductive reasoning uses patterns. Deductive reasoning
Uses facts.
uses facts. That might be the key word for deductive reasoning. Facts or rules or laws or whatever it happens to be. In math, it's usually rules, theorems, postulates, axioms, corollaries, whatever kind of mathematical rule it might be. While we're looking at this, what did I say earlier in the year about all of those? They're all the same thing. Axioms, corollaries, postulates, we're going to consider them all the same thing. They're not really, but that's what we're going to consider. Anybody have any idea what a corollary might be? You might have heard a word.
Correlation.
It's correlated to something, right? So a corollary is actually a rule that's built off of some other rule. Like the distance formula that we have here, what was it built off of?
The points.
Some theorem. The only theorem you probably know. Pythagorean's theorem. It was built off of Pythagorean's theorem. So the distance formula is sort of like a corollary. It's something that came from Pythagorean's theorem. What do you know about all those? How do they differ from theorems? Anybody remember that? Theorem, you have to what?
You have to get a rule.
It's got to be proven. These what?
Prove
Do they have to be proven? No, you just take it for granted. Take it for granted that they're true. These we just take for granted are true. Theorems have to be proven. Law of detachment. Going to talk about two different laws in that. One of them is law of detachment. I'll give you a second to write this down. And then I'll explain it. Write it down just like it is up there. I know kids just try thinking, and you're right, it does. It looks sort of like it's not going to make much sense. Also, while you're writing, don't forget to have your parents checking their emails. Sent that stuff out. So check your email. If they didn't get something, you need to come tell me, because apparently the email's not what I thought it was. We need to fix it so you can get those extra credit points. I know when those papers got filled out, none of you would actually just flat out lie about what your parents' email address was, right, Mr. Ray?
It's not nice to me, yeah.
Huh?
My bad, I was there too. I'm embarrassed.
With law of detachment, what's the word detachment mean?
It's
Not
not
attached to one.
So take apart. That's what you're doing with the law of detachment. And these two laws will confuse a whole bunch of you. With the law of detachment, if you listen right now, I don't think either one of these two laws is all that difficult. You just have to know what I'm getting ready to say right now. They're going to give you a statement. That's our statement. If P, then Q. Makes no sense, but I'm telling you that statement is true. All right? So I'm telling you if P, then Q is a true statement. No matter what it means, it's true. If we take that statement and we detach it, take it apart, the two parts, we have a hypothesis and a conclusion. We take them apart, and this hypothesis all by itself is true. Guess what's true about the conclusion all by itself? It's true. So if you got a statement, if and then statement, and the whole thing starts off being true, take it apart. The first part of it's true, standing over here all by itself. Guess what has to be true about the second part of it?
Must be true.
Must be true. So, I have these two pins, right like this. I tell you that this is a true statement. All right? Doesn't make any sense, does it, Kelsey? Doing it? These two pins are a true statement together. Okay? This is our hypothesis. On this side, let me turn around here so I don't. This is our hypothesis, the brown one. The black one's the conclusion. I take them apart, and we look at the brown one and say, hey, it's true. What's that tell us about the black one all by itself? It's got to be true. All right? Now, it doesn't work the other way around. If I tell you it's true this way, and then I take them apart and I say the black one's true, does that tell us that the brown one is true? No, it only works if we know it in this order. Whole thing's true, the hypothesis all alone is true, then we can conclude that the conclusion must be true.
Does that mean it would pretty much have to be like instead of like or, because or necessarily not both?
Sorta, but it's sorta, but it's a sort of different kind of statement. Which question, Dalton? Or Dawson?
Have you ever seen like an if be true and then not be true?
It could be. So if I say something like, if acute angle, then 150 degrees. That's not true, is it? All right? So that's not true. The whole statement's not true. So could we do the law of detachment with it? No, because the very first thing is the whole statement has to be true. All right? So if we said something like, if angle 1 is acute, and then we say, then measure of angle 1 could be 20 degrees. All right? That's a true statement. We take it apart, and I tell you, this part is true. All right? I'd have to tell you that. Angle 1 is an acute angle. Then what's that tell us about that second part? That's true also. All right? That's the law of detachment. You take the two parts, hypothesis and the conclusion apart. If the original statement, the whole thing together was true, if this part all by itself is true, then that means the second part all by itself has to be true.
What if like the whole thing's false?
The whole thing was false from the beginning right here, then we can't use that law. You just say it doesn't, you can't do it. I'm listening.
The last part could be false.
Yeah, on my state, mine wasn't very good. See? I was hoping nobody'd catch on to that, Ginger. Quit being smart. Here's a better example. If two segments have the same length, they are congruent. Is that true? You got two segments that have the same length. Are they congruent? Yeah. Then we look at this. These two segments are equal to each other. What's that tell us about them? They have the same length. So that part all by itself is true. What can we conclude from that? Then they have to be congruent to each other. Then segment AB has to be congruent to segment QR. Look real quick to make sure you understand this. When I use an equal sign, what did I leave off? The symbols, right? You don't need the symbols because the only two things that can be equal to each other are segments, right? No lines, no rays. They can't be equal. When I use the congruent symbol, I want to put the symbols on there, the segment symbols on there. Let's go back. Let's try to make up something else.
Good.
Give me something. Let's say something. If what? Give me something geometrical so we can make sure that it's true. If angle 1, go ahead. What?
I was gonna say
It's 73 degrees.
Equals 73 degrees.
The angle.
Then what do we know about it? Then angle 1 is acute. This one's not a very good one. You guys just copied off of. Let's find something different. You guys copied off my
I
last
don't know.
one.
Are you like for the one like?
If angle 1 is congruent to angle 2, then angle
What about this? If angle 1
Yeah, good start.
is part of a supplementary like pair, then
So if we say angle 1 is supplementary to angle 2,
then they add it to and they add it
then add to 1/8. So that's our first statement. And that's a true statement, right? If I split that apart and I say angle 1 is supplementary to angle 2, that all by itself is true. So I'm telling you, angle 1 and angle 2 are supplementary. What conclusion can you draw from all that?
Yeah.
Then angle 1 and angle 2 have to add up to 1/8.
I wanted the first one.
It
goes-
didn't work. It's
it-
supposed to be copied.
It doesn't completely work because we can't, just because angle 1's 73 degrees, is that the only acute angle there is in the world?
If it's a,
And that's what Ginger started to say a little while ago, and I was trying to get away from it before she said it.
if it just said, angle 1 is less than 90 degrees, then it would work.
If we would have said, if angle 1 is 0 to 90 degrees, then it is acute angle. That would have worked that way. Looking at this one, I skipped up ahead of me, didn't I? Went too far. Law of syllogism. Law of syllogism. Another law. Write this down. I'll give you a second to write it down.
It's a weird name.
Do what?
It's a weird name.
Yeah. Up till like last year, I wouldn't even say it. I'd just say the other law or something. Syllogism. I don't even know if I'm pronouncing it right or not, but I know it's not gonna matter if Dawson's not writing it down. He's not gonna know it. Right.
It's not the definitions, but I wrote the law, the title.
Stuff so you understand. Law of syllogism's probably a little easier, because if there's not a certain pattern, it for sure won't work. And you've dealt with that pattern in other math courses. Does anybody see a pattern in this first part here? With our two statements?
They both have Q.
They both have Q. Now, that's true And that's sort of where we need to be, but you need a little more.
Well, he was an end statement. Statement.
Do you see how that is? In algebra, you probably learned something like this. A equals B and B equals C, then what conclusion could you draw? A equals C, right? Notice how they both had the B's. B was the end here, the beginning there. Same thing here, and it's got to go in that pattern. So whatever the conclusion is here has to be the hypothesis in the next statement for the law of syllogism to work. So if I say this, if Fred, then Joe, that's my first statement. If Joe, then Tom, that's my second statement. What's the conclusion that we can draw using the law of syllogism? If Fred, then Tom. But notice, Joe had to be there, Joe had to be there. So what if I wrote this? If Sally, then Ann. If Sally, then Eva. What conclusion can we draw there? None. And that's what you write. No conclusion, or no conclusion is possible, whatever it is, however you want to write it out. All right? We can't draw a conclusion here because it's in the wrong order. It's in the wrong order. Let's use geometry. If angle 1 supplementary to angle 2, then they add up to 180. If angle 3, plus angle 4 is 180, then they are spider angles. What conclusion can we draw from that? You know, it doesn't make any sense. Does it go in the right order? Does it have 180 here, then 180 here?
Yeah.
So that tells us then this part, along with that part, would have to be true. All right? We go back to this. If horse, then bell. Cover this up. If horse, then bell. If bell, then airplane. What conclusion can we draw? If horse, then airplane. Law of syllogism.
Okay, so going back to the one where it was Sally, then Ann, then Sally, then Eva. If Sally and Ann were a biconditional statement, then could you use the converse to know that
Then it would
Eva
work.
is true?
Yeah. So if they said something like this, Sally and, where you could switch it around either way, then when they said Sally, Eva, we could switch this one around and then use the law of syllogism to say and Eva.
No, even if it like was just Sally and Sally Eva without the biconditional, couldn't you combine those and make it Sally and Eva?
Not necessarily.
But could it be a possibility?
Maybe,
Right.
but it's not a conclusion that we can draw from it.
Okay.
Because there's going to be, I don't know if I can think of one right off the top of my head. Well, when we were doing the angles, and I put 73 degrees in there and said it was acute, does that mean that all acute angles are 73 degrees?
No.
Not necessarily. So if I did this, angle 1, 73 degrees. Angle 1 is acute. Just from that, even though I come down here and I say angle 2 is acute, does that necessarily mean that angle 2 has to be 73 degrees?
Nope.
Not necessarily. So you gotta be careful.
Take a picture of that.